This video is about graphing rational functions. The warm-up will talk about limits. So the limit as this function goes toward negative infinity for x is going to be the same as what happens when the limit of the function goes toward positive infinity for x, and that's going to be at the horizontal asymptote of this function. So these limits are both 4. The limit of this function as x approaches 3 from the right is going to be positive infinity. The limit of this function as x approaches 3 from the left will also be positive infinity. The limit as f of x, the limit of f of x as x approaches negative 3 from the left would be from this way, from the left, so that's going to be negative infinity. Then as x approaches negative 3 from the right, the function is going up to infinity. So that's just a reminder of that stuff. And then, just like last year, we talked about graphing rational functions. So today's video is primarily a way to remind ourselves of some of the things we need in order to get a good sketch, a good graph of a rational function. And then we're going to practice some of these. So we need to figure out where the function has removable discontinuities or holes. This occurs anytime there's an x value that makes both the numerator and denominator equal to 0. Usually, after you figure this out, then you can simplify the function by canceling anything that is in both the numerator and denominator. And then the rest of the time, you can just use the simplified function. So after finding any holes, then you can cancel things off and simplify. Then you also need to find vertical asymptotes where only the denominator is equal to 0, so values for x where that's the case. X-intercepts are where only the numerator is equal to 0, so x values for that. Horizontal or oblique asymptotes are finding the behavior of the function as x approaches positive and negative infinity. And then there's other useful information that'll help you graph, like the y-intercept and does the function cross the horizontal asymptote, and if so, can we figure out where that is? So let's take a look at some problems. Problem 1, we have x minus 3 over 2x squared minus x minus 15. Usually the first thing we want to do is factor. So if we factor the denominator, we end up with 2x plus 5 and x minus 3. So what we notice is there is a value of x that makes both the numerator and denominator equal to 0. That value is at x equals 3. So there's going to be a hole where x equals 3. And then we actually need to find the y value for that. So what we're going to do is we're going to cancel off and reduce the fraction, simplify it by canceling the x minus 3's. And so basically, this function r of x behaves like 1 over 2x plus 5 at every spot except for where x equals 3. When x equals 3, there is a hole or removable discontinuity in the function. So if I substitute 3 into this equation, I get 1 over 11. So at 3, comma 1 over 11, there is a hole. So 3 1/11th, there is a hole. Then let's look for vertical asymptote. Vertical asymptote is where the denominator and only the denominator is equal to 0. So I would set 2x plus 5 equal to 0. I would get the line x equals negative 5 halves. So at x equals negative 5 halves, I have a vertical asymptote. The x-intercept would be where only the numerator is equal to 0. We can look at the simplified form and we figure out that there is no such value where only the numerator is equal to 0 because there's no x up there, it's just a constant. The y-intercept would be what happens when we substitute in x equals 0. So if we substitute in x equals 0, we get 1/5. We also could have done that at the very beginning of the problem. If you substitute x in as 0, you get -3 over -15, which is also 1/5. So the y-intercept is at 0, 1/5, which is also a pretty small value. And then we can determine the horizontal asymptote. We look at this function, either the simplified or unsimplified version. We see that the power on the bottom is bigger than the power on the top. So that means that our horizontal asymptote is going to be the line y equals 0. And then that will give us pretty much everything we need in order to graph this function. So I just kind of trace where all the points are. I realize that as I go up toward this vertical asymptote, I'm going to go off to infinity. And then, since the bottom 2x plus 5 is to the first power, anytime I have something to the first power, the behavior near the asymptotes is going to be such that on one side it goes one way, and on the other side it's going to come from the other direction. Since there is no x-intercept, it never crosses the x-axis, and this is what our graph would look like. If we take a look at what Desmos graphed, we have a very similar situation: 3, 1/11, 0, 1/5, and then this vertical asymptote at -2.5. Here's a bonus problem that's not on your notes page. I'm going to go through some of these a little bit quicker now, because we've already talked about some things. So first thing I will do is I will factor this function. So the top has a GCF. And then we'll factor the numerator and denominator further. So I have 2 times x plus 4, x minus 2. And the denominator is x plus 3 times x minus 2. So what I'm going to notice is that there is a hole in this function. The hole occurs at x equals 2. So I can cancel this off and get a simplified version of this function. Then I can substitute in 2 into the simplified version of this function to figure out what the actual y value of that hole would be. So if I substitute in 2, I get 12 over 5. So at 2, 12 over 5, there's a hole. 12 over 5 is about 2.4. Vertical asymptote is going to be at x equals -3. It's where the denominator equals 0. X-intercept is where only the numerator is equal to 0. So that's at -4, 0. Y-intercept is what happens when I substitute in 0 for x. I would get 8 over 3. And then the horizontal asymptote is, since the powers are the same, I divide the leading coefficients, which is 2 divided by 1. So my horizontal asymptote is going to be y equals 2. Then I can graph the function. I know that I have the y-intercept at not quite 3. I graph here. There's a hole that I have to be slightly careful of, and it's going to look something like that. Here's another example. I forgot to put the hole on the graph when I did it on Desmos, but this is what the graph would look like. Problems 2 and 3. Problem 2 doesn't need any factoring. There is no hole, as nothing cancels off on the top and bottom. Vertical asymptote is at x equals 5. X-intercept is where only the numerator equals 0, so that's at -4, 0. Vertical asymptote at 5. Y-intercept occurs at When I substitute in 0 for x, I get 4 over negative 5 squared, which is 4/25. So that's a pretty small value. And then the horizontal asymptote would be at y equals 0 because the power on the bottom is an x squared. If I multiplied this out, I would see that it's x squared minus 10x plus 25. Power on the bottom is clearly bigger. So that means y equals 0 is the horizontal asymptote. Now notice that this function does cross the horizontal asymptote at x equals -4. So what I'm going to end up with here is a function that looks something like this. It's going to cross at -4 and then come back toward the horizontal asymptote. And then since this denominator is squared, notice that both end behavior, or I'm sorry, not end behavior, both vertical asymptote behaviors are going to go in the same direction. Now also, we can kind of think about this pretty logically. To the right of -4, this function will always be positive, except for at 5, where it's undefined. But then after -4, the function will be negative. This is something that we discussed a lot when we were talking about the inequalities of rational functions. So this is kind of what the graph would look like. Problem 3, I'm going to factor. So if I factor the bottom, I get x plus 6 and x plus 3. There is no hole. Vertical asymptotes, there's 2 of them, at x equals -6 and x equals -3. There is an x-intercept where the numerator is equal to 0. So that would be at, if I solve for x, when I set the numerator equal to 0, x equals 1/2. So I would write that as a point, 1/2, comma 0. Y-intercept is 1/18 if I set x equal to 0 and see the 1 over 18. Horizontal asymptote would again be y equals 0. So once again, the function actually crosses the horizontal asymptote right there. So my y-intercept is pretty low. I have these points, crosses, and then comes back toward the line. Notice that neither the x plus 6 or the x plus 3 is squared. So that means that the function will approach the vertical asymptote in different ways. Notice that there is not anything that crosses the x-axis here. There was no x-intercept in between. So can't cross. It has to come back down. And then the behavior of the function at the vertical asymptote will be going in different directions. And then we will approach the horizontal asymptote as we go off to infinity. If we check, see what Desmos says about these graphs, we have something very similar. One other thing to note, Desmos indicates that this graph does not get that close to the x-axis, but there's no way that we really expect you to be able to figure that out. So as long as the behavior is what we're looking for, where it approaches the asymptote in the right spot and we don't have any x-intercepts or anything, we understand that you're not going to get the exact location of where it starts turning around perfect. 2 more questions. Let's factor number 4. So if we factor the numerator, we get 3x and 1 and then x and 1. So I would have to put a minus here and a plus here in order to make things work. Then the bottom factors to x minus 2, x plus 1. So once again, there's no hole. There's 2 vertical asymptotes at 2 and -1. There are 2 x-intercepts, -1/3, 0, and 1, 0. There's a y-intercept at 1/2 if I substitute in x equals 0. I get -1 over -2, which gives me 1/2. And then there is a horizontal asymptote at y equals 3, because if I look at the powers are the same, I divide the leading coefficients. So now I'm going to start graphing all of these things. So 2 and -1 are my vertical asymptotes. I have x-intercepts at -1/3 and +1. I have a y-intercept at 1/2, and then I have a horizontal asymptote at 3. So I pretty much have a lot of this figured out. Like, it's not going to cross horizontal asymptote because it has to, at least in between these two asymptotes, because it has to hit both of these x-intercepts in here. So now the other thing that we have to do is we have to figure out, does this function actually cross the horizontal asymptote? And that's something that we haven't actually done yet. The way that you can figure that out is by setting the function. So 3x squared minus 2x minus 1 over x squared minus x minus 2. Set the function equal to the horizontal asymptote and see if it actually works. So let's set it equal to 3. Is this function ever equal to 3? Well, I'll multiply the x squared minus x minus 2 over. So I have 3x squared minus 2x minus 1 equals 3 times that whole thing. So 3x squared minus 3x minus 6. And then just solve this equation, which is pretty straightforward. So 3x squareds are going to cancel when I subtract things over. I'm going to add the 3x over. So 3x over to this side, that equals x. Then I'm going to add the -1 over. And I get at x equals -5, y equals 3. So -5, comma 3 is actually a point on the graph. So it's going to hit this point and then come back up toward the horizontal asymptote. And over here, it never hits the horizontal asymptote. So this is kind of what my graph looks like. Finally, the last problem, we'll similarly factor. So factor the numerator, factor the denominator. And then I once again realize I have no holes. I have a vertical asymptote at x equals 3/2, and x equals -6. So 3/2 is actually a positive number. So that might be something that is important for a math teacher to know. And then at -6, x-intercepts are where only the numerator is equal to 0. So that's going to be at -7, and 2, y-intercept is what happens when you sub in x equals 0. So you get -14 over -18, which is 7/9. Horizontal asymptote is going to be y equals 1/2. And that's because when you sub in, when you look at the leading coefficients, since the powers are the same, you get 1 over 2. So put 1/2 in. 7/9 is a little bit above 1/2. You get an x-intercept at -7, an x-intercept at +2. And then the last thing we have to do is check to see if this function intersects one of these vertical asymptotes. I'm sorry, not vertical asymptotes. If it intersects the horizontal asymptote of 1/2. So I'm going to set 1/2 equal to the function. Because if the function ever equals this y value, it would have to be where 1/2 is equal to the y value. So then I multiply the 2x squared minus 9x minus 18 over to the left. And I multiply the 2 over to the right. So I basically just cross multiply this. The 2x squareds go away. I subtract the 9x over and I get 1x. I add the 28 over and I get 10. So x equals 10, comma 1/2 is a point on the graph. And now I just figure out where everything goes. I have a y-intercept. It doesn't cross my horizontal asymptote in that spot, so I should probably use a different color, but it's going to go off to infinity, doesn't cross, comes back up. Notice that neither of these is squared over here, so because neither of them is squared, the behavior near the vertical asymptotes is going in opposite directions. It crosses the x-axis there, but doesn't go over 1/2. Crosses the x-axis here, hits 1/2 at 10, and then is going to come back down toward 1/2 at the end. And so you see that that happens on Desmos as well. We have our asymptote hitters, and then after it hits the asymptote, it's going to come back down toward 1/2 as we go off to infinity.